Today is our fifth chapter and it's called Thermal Effects. In this chapter, we're going to be learning about solids, liquids, and gases, energy of particles, the Celsius scale in temperature, and thermal expansion. Also, we're going to be learning about conduction, convection, evaporation, boiling, and condensation. Lastly, in this chapter, we're going to be learning about specific heat capacity and latent heat. So let's begin thermal effects by first understanding solids, liquids, and gases. So, every material is a solid, a liquid, or a gas, and scientists have developed a model called the kinetic theory to explain how solids, liquids, and gases behave. So, according to this theory, matter is made up of tiny particles which are constantly in motion. These particles attract each other strongly when close, but the attractions weaken if they move further apart. So, this is the kinetic theory. This is the description, the model scientists have developed to explain how solids and liquids and gases behave. Now, let's see what a solid is. So, a solid such as iron has a fixed shape and volume, and its particles are held closely together by strong forces of attraction called bonds. These are chemical bonds. Like in the previous chapter, we were reading chemical energy that is inside these bonds that make these bonds basically. So these are the bonds that makes particles get held closely together. So the particles vibrate backwards and forwards but cannot change positions. So this is the structure of a solid, that the particles are held closely together by strong forces. They're not weak. They're strong forces of attraction, and they can only vibrate about their positions, but they cannot move. Whereas a liquid such as water has a fixed volume but can flow to fill any shape. Solids have a fixed shape and also a fixed volume, but they cannot fill any shape. They have their own shape. A liquid, whereas such as water, has a fixed volume, but they can flow to fill any shape. The particles are close together and attract each other, but they vibrate so vigorously that the attractions cannot hold them in fixed positions, and they can move past each other. So this means that the bonds between the liquid molecules are weaker than a solid molecules. Even though the particles of liquids are close together and they do attract each other, but because the attractions of their molecules cannot hold them in fixed positions. That's why they move past each other when they are heated up. So when they vibrate, they move past each other. This never changes its place. It stays where it is and just vibrates back and forth. They never change positions. Liquid molecules have weaker bonds compared to a solid, and a liquid can flow to fill any shape, whereas a solid has a fixed shape. Now, third, we have gas. A gas such as hydrogen has no fixed shape or volume and fills any space available. So this is totally different from both the solid and the liquid. The gas has neither any fixed shape nor any volume, and it fills any space available. Its particles are well spaced out and virtually free of any attractions. This means that the bonds between its molecules are so much weaker, even more weaker than liquids, that they are virtually free of any attractions. So the particles of gases are well spaced out. They move about at high speed, colliding with each other and the walls of their container. This means that the molecules have a lot of space between each other and they move about at high speeds. So this was gases. So what are particles? Let's just think about that for a moment. As you all know, everything is made from about 100 simple substances called elements. The elements we read in the periodic table as well. So an atom is the smallest amount of an element. In some materials, the moving particles of the kinetic theory are atoms. But however, in most materials, there are groups of atoms called molecules, like methane. So this is what we mean by particles. By particles we mean molecules or atoms. If sometimes it's atoms and sometimes it's molecules, but if we're talking about water, then of course we're talking about molecules when we say particles, because water, the formula of water is made up of atoms. So water is basically groups of atoms, H2O, 2 hydrogen atoms and 1 oxygen atoms, and we get water. So we're not going to call it atoms. By saying particles we mean molecules. Whereas hydrogen, when we say particles, we can say that we're talking about the atoms of hydrogen. Okay, so anyways, now that we've understood solids, liquids and gases, we're going to move ahead on to understanding the energy of particles. Particles, atoms or molecules, whatever you want to say. So, the particles, atoms or molecules in solids, liquids and gases have kinetic energy because they are moving. We know that. This is the kinetic theory. However, they also have potential energy because their motion keeps them separated and opposes the bonds trying to pull them together. So, the particles in gases have the most potential energy because they are furthest apart. Okay, so the total kinetic and potential energies of all the atoms or molecules in a material is called its internal energy. The hotter a material is, the faster its particles move and the more internal energy it has. They have potential energy because their motion keeps them separated and opposes the bonds trying to pull them together. And they have kinetic energy because they are moving. So, if a hot material is in contact with a cold one, the hot one cools down and loses internal energy, while the cold one heats up and gains internal energy. So the energy transferred is known as heat. We use the word heat in our daily language, and it basically means thermal energy, but we can say it's heat. The term thermal energy is often used for both internal energy and heat. So now that we've understood the energy of particles, the very new thing that we understood here was internal energy. And what is internal energy? Kinetic plus potential energy is internal energy. The total kinetic and potential energy of all the atoms or molecules in a material is called its internal energy. So this is what we just understood here. And the hotter a material is, the faster its particles are moving and the more internal energy it has. So now that we've understood the energy of particles, we are ready to go forward and understand the Celsius scale. The Celsius scale is a temperature scale with a range of numbers for measuring the level of hotness. Everyday temperatures are normally measured on the Celsius scale. We're talking about the thermometer here. The thermometer has the Celsius scale, so temperatures are normally measured on this Celsius scale. Its unit of temperature is the degrees Celsius. This is the symbol we use to represent it. The numbers on the scale were specially chosen so that pure ice melts at 0 degrees centigrade and pure water boils at 100 degrees centigrade under standard atmospheric pressure of 101,325 pascals. So these are its two fixed points. Temperature below 0 degrees centigrade have negative values. We say -1, -2, -3. The bigger the number of the negative, the lower the temperature would be. Actually, we say minus values, we don't say negative. -12 degrees centigrade, like that. So let's go ahead and look at the thermometer here. So temperature is measured using a thermometer, as we all know, of course. One simple type is shown like here. You can see this thermometer. So as you can see, the glass bulb of this thermometer contains a liquid, either mercury or colored alcohol. This is the glass bulb. This liquid expands when the temperature rises and pushes a thread of liquid further along the scale. So every thermometer depends on some property of a material that varies with temperature. By property we can say characteristic. So the thermometer, like this, as you can see, this contains a liquid whose volume increases with temperature. The two thermometers we can see here use materials whose electrical properties vary with temperature. Sorry for this mistake here. I was wanting to write vary, V-A-R-Y. Right now it is written very. So sorry for that. What we are just understanding here is that every thermometer, it depends on some property of a material that varies with the temperature. Like this one contains a liquid whose volume increases with temperature. And these two, as you can see, use materials whose electrical properties vary with the temperature. All thermometers agree at the fixed points, which is 0 degrees centigrade and 100 degrees centigrade. 0 degrees centigrade and 100 degrees centigrade are the fixed points of a thermometer. So all thermometers agree at these fixed points. However, at the temperatures, they may not agree exactly because their chosen properties may not vary with temperature in quite the same way. Which means that maybe this thermometer would show a different reading from this thermometer, because their chosen properties may not vary with the temperature in quite the same way. So, but let me tell you, the difference is not going to be huge, okay? It's going to be just a small difference, and that's normal. They both will still show the right readings. So here we have a thermistor. This is a thermistor thermometer. So the thermistor is a device which becomes a much better electrical conductor when its temperature rises. This means that a higher current flows from the battery, causing a higher reading on the meter. Then we have the thermocouple. Thermocouple thermometer. Two different metals are joined to form two junctions in this thermometer. A temperature difference between the junctions causes a tiny voltage which makes a current flow. The greater the temperature difference and the greater the current would be. In any object, the particles, atoms or molecules are moving. So they have kinetic energy. They move at varying speeds, but the higher the temperature, then on average, the faster they move. So temperature is not the same as heat. For example, a spoonful of boiling water has exactly the same temperature, 100 degrees centigrade, as a saucepan full of boiling water, but would store far less thermal energy, which is heat. So basically, a spoonful of boiling water has the same temperature as a saucepan full of boiling water. But because it's less, then it will store far less thermal energy compared to the saucepan full, because there is more water in the saucepan compared to a spoon. But both have the same temperature because the water in both of them is boiling. So both of it has the same temperature, which is 100 degrees centigrade. So if a hot object is placed in contact with a cold one, there is a transfer of thermal energy from one to the other. So as the hot object cools down, its particles lose kinetic energy, and as a cold object heats up, its particles gain kinetic energy. So when both objects reach the same temperature, the transfer of energy stops because the average kinetic energy per particle is the same in both. So from this we conclude that objects at the same temperature have the same average kinetic energy per particle. The higher the temperature, the greater the average kinetic energy per particle. So now that we've understood temperature, we've also understood that temperature is different from heat, and that objects at the same temperature have the same average kinetic energy per particle. And the higher the temperature would be, the greater the average kinetic energy per particle would be as well. So now let's look at the absolute zero and the Kelvin scale of the temperature. So as the temperature falls, the particles in a material lose kinetic energy and move more and more slowly. So at minus 273 degrees Celsius, they can go no slower, which means that they cannot lose any more kinetic energy. So this is the lowest temperature there is, and it is called the absolute zero. The rules of atomic physics do not allow particles to have zero energy, but at absolute zero they would have the minimum energy as possible. So this is the absolute zero. It's like the minimum energy. The minimum energy particles can have. This is the lowest temperature there is. That at this temperature, the particles cannot lose any more energy. This is called minus 273 degrees Celsius. It's called the absolute zero. Now, in scientific work, temperatures are often measured using the Kelvin scale. It's not the degree Celsius, it's the Kelvin scale. So its temperature unit, the Kelvin, which is represented by a capital K, is the same size as the degree Celsius, but the scale uses absolute zero as its zero. The Kelvin, the unit, is equal to the size of the degree Celsius, but the only difference between them is that the Kelvin scale uses the absolute zero, which is minus 273 as its zero. So 0 Kelvin that represents minus 273. But yes, you can convert from a Kelvin temperature into a degree Celsius temperature. This is the equation we use to convert from one scale to the other. Celsius temperature plus 273 is equal to Kelvin temperature. Then of course we rearrange the equation to get the desired answer. For example, to get the Celsius temperature, we would have to minus 273 with the Kelvin temperature, and we will get the same result. We would get the temperature in degrees Celsius. So this is the equation we use to convert from the Kelvin temperature to the Celsius temperature, or the Celsius temperature into the Kelvin temperature. So the minus 273 degrees Celsius is equal to 0 Kelvin. The absolute zero of both the scales. Celsius scale has minus 273. This is the absolute zero of Celsius scale. And of Kelvin scale, it is 0 Kelvin. The temperature at which ice melts is 0 degrees Celsius and 273 Kelvin. And the temperature when water boils is 100 degrees centigrade and 373 Kelvin. So it can be a little confusing, this Kelvin scale, but this is what it is. Basically, minus 273 represents 0 Kelvin. 0 Kelvin is equal to minus 273 degrees Celsius. And that's how the temperature at which ice melts becomes 273 Kelvin, and the temperature at which water boils becomes 373 Kelvin. So, where greater accuracy is required, absolute zero is taken to be minus 273.15 degrees Celsius. It's a even more accurate measurement. Minus 273.15 comes in. So the Kelvin scale is a thermodynamic scale. It is based on the average kinetic energy of particles rather than on a property of a particular substance. So this was it for temperature. We understood the different scales of temperature. We understood also about thermometers. So let's just now move ahead on to understanding thermal expansion. If a concrete or steel bar is heated, its volume will increase slightly. This effect is called thermal expansion. If anything is heated, its volume increases slightly. Most solids expand when heated, and so do most liquids, and by more than solids. For example, if a liquid is stored in a steel container, a space must be left at the top to allow for expansion, because liquids expand when they are heated. So there should be some space left at the top to allow for expansion. So the kinetic theory explains thermal expansion as like this. When, say, a steel bar is heated, its particles speed up. So their vibrations take up more space, so the bar expands slightly in all directions. If the temperature falls, the reverse happens and the material contracts, which means it gets smaller. So this was thermal expansion. When a steel bar or any material is heated, its particles speed up, so the vibrations of these particles take up more space because they're moving, so they are taking more space. So the material expands slightly in all directions. The effect may not be very noticeable, but it happens if we measure it. But if the temperature falls, the reverse happens and the material contracts, which means it gets smaller. Say for example, we have some balloons and we try to fit these balloons into a smaller space. It's difficult to do that because the balloons take more space. But if we add liquid nitrogen to these balloons, then because of liquid nitrogen, they contract. So basically what happens is liquid nitrogen is cold, so the temperature falls down and the material of the balloon contracts, so it gets smaller and smaller and they fit into a small space. This is a fun experiment you can do to test out thermal expansion. Moving ahead, when choosing materials for particular jobs, it can be important to know how much they will expand. So here we have two examples. First one is steel rods can be used to reinforce concrete because both materials expand equally. But if the expansions were different, the steel might crack the concrete on a hot day. So, steel rods are used to reinforce concrete because they both expand equally. The second example is that if an ordinary glass dish is put straight into a hot oven, the outside of the glass expands before the inside, and the strain cracks the glass. Sometimes we allow for expansion and contraction as well. Like when overhead cables are suspended from poles or pylons, they are left slack, partly to allow for the contraction that would happen on a very cold day. So yes, when the temperature falls, materials contract as well. We just read it before. An example for allowing for expansion is gaps are left at the ends of bridges to allow for expansion. So one end of the bridge is often supported on rollers so that movement can take place. Because concrete expands on hot days. Now, here as you can see in this thermometer, the liquid in the bulb expands when the temperature rises. So the tube is made narrow so that a small increase in volume of the liquid produces a large movement along the tube. So the thermometer is an example of using expansion. We can use expansion in many other different ways as well. Like, firstly, this was the example because the liquid in the bulb expands when temperature rises. So when the liquid expands, it tells us the reading of the thermometer. The second example is the bimetal strip. So in the bimetal strip, thin strips of two different metals are bonded together. Like in this example, we have brass and steel. So what happens is that when the strip is heated, one metal expands more than the other, which makes the bimetal strip bend. As you can see, the brass expands more than steel. That is why when it is heated, the bimetal strip is like this. And when it is cooled, the brass contracts more than steel, so it becomes something like this. Bimetal strips are used in some thermostats devices for keeping a steady temperature. As you can see here, when it is on, it's like this. When the temperature is normal, the bimetal strip is straight. But if the temperature increases, the bimetal strip bends and the circuit is switched off like this. So the thermostat is controlling an electric heater. What happens is that when the temperature rises, the bimetal strip bends. The contacts separate, as you can see, like here as you saw, the contacts have separated and the current to the heater is cut off. So when the temperature falls, the bimetal strip straightens up and the current is switched on again. In this way, an approximately steady temperature is maintained. Well, more modern designs often use an electronic circuit containing a thermistor rather than a bimetal strip. But the bimetal strip is an example of using expansion. Okay, now let's check out something totally different over here. Water and ice. So, when hot water cools, it contracts. However, when water freezes, it expands as it turns into ice. That's totally different from what we just learned previously. What happens is that in liquid water, the particles are close together, but in ice, the molecules link up in a very open structure that actually takes up more space than in the liquid. So you can see here, in ice, the molecules are arranged in a structure, and this structure is open. So the molecules are further away from each other compared to the liquid molecules. So this is the difference between liquid and ice. The force of the expansion can burst water pipes and split rocks with rainwater trapped in them. So we also know ice has a lower density than liquid water. In other words, each kilogram has a greater volume because there are less molecules in each kilogram. So that is why ice is less dense than water. It has less mass in a particular volume compared to water. So because of its lower density, ice floats on water. So when liquid water is cooled, the molecules start forming into an open structure at 4 degrees centigrade, just before freezing point is reached. As a result, water expands very slightly as it is cooled from 4 degrees centigrade to 0 degrees centigrade. It takes up least space and therefore has the maximum density at 4 degrees centigrade. Unlike a solid or liquid, a gas does not necessarily expand when heated. That is because its volume depends on the container it is in. So when dealing with a fixed mass of gas, there are always 3 factors to consider: the pressure, the volume, and the temperature. Depending on the circumstances, a change in temperature can produce a change in the pressure or volume or both. So here we're going to now look at how pressure changes with temperature at constant volume. So this means that the volume is going to be the same, but the temperature is going to be increased. And we're going to check if the pressure increases as well. So as the temperature of the air rises, so does the pressure. This is because molecules move faster. There's a greater change in momentum when they hit the sides of the flask, so a greater force. The trapped air over here has a fixed volume. What happens is when the temperature of the air rises, the pressure also increases because the molecules of the air hit the sides of the flask more often. So the pressure increases. We can measure this on a pressure gauge, and here we have the results of this experiment. So when temperature was 20 degrees centigrade, the pressure was 102 kilopascals. When the temperature increased, the pressure also increased, and so on. When it was 80 degrees centigrade, the pressure increased to 123 kilopascals. And when it increased to 140 degrees centigrade, the pressure increased to 144 kilopascals. And when the temperature was 200 degrees centigrade, the pressure was 165 kilopascals. So the cylinders used for storing gas are strong enough to withstand any extra pressure due to normal rises in temperature. So this is also the reason why it is dangerous to throw aerosol cans on bonfires, because they might burst because of the increase in pressure. However, that is mainly because of the liquid propellant in this can turns to gas. In the same way, we can see how volume changes with temperature at constant pressure. So what happens is that, say for example, we have 2 volumetric flasks. Trapped air is heated at constant pressure. This is atmospheric pressure because only the short length of the pressure, the liquid, separates the air from the atmosphere outside. So as the temperature increases, the volume of the gas increases as well, so the gas expands. So what we are basically saying is, if the pressure is kept constant, then when the temperature would increase, the volume would also increase because the gas expands, so the volume also increases. We can compare expansions of solids, liquids, and gases as well. So at constant pressure, gases expand much more than liquids, which in turn expand more than solids. For example, for the same volume of material and the same rise in temperature, starting at room temperature, water expands 7 times as much as steel. Air at constant pressure expands 16 times as much as water. So it is the strength of the attractions between the particles that make the difference. So in a solid, the attractions are very strong. We all know that. We just read it in the beginning. If the temperature rises and the particles move faster, this has very little effect on the separation because they are so tightly held together. Whereas in liquid, the attractions are weaker, so the expansion is greater. But it's not greatest, it is only greater than a solid, but it is still less than a gas. So in a gas, the attractions are extremely weak, so the expansion is much more than the liquid, more than the solid. It is the maximum expansion. The gas can expand the maximum compared to solid and liquids. So here I have an example. Balloons are filled with cold air or using a motorized fan. I'm talking about the hot air balloons. So they are filled with cold air using motorized fan. It is easier to fill with that. Then a gas burner raises the temperature of the air to 100 degrees centigrade or more. So there is no change in pressure. It stays at atmospheric, but a large increase in volume. So when the gas is heated inside the balloon, the gas's volume increases. And that is how the hot air balloon gets filled up with gas. So this was the link between temperature, pressure, and volume. Now that we've understood this and we've understood what thermal expansion is, how we can use thermal expansion, the kinetic theory explaining the thermal expansion, we can move ahead onto understanding conduction. So, we all know that all materials are made up of tiny moving particles, which are called atoms or molecules. The higher the temperature, the faster the particles move. We also know this. We also know that the higher that the temperature is, the faster the particles move. So, we have a metal bar, for example. If one end of a metal bar is heated, the other end eventually becomes too hot to touch as well. What happens is that heat is transferred from the hot end to the cold end as the faster particles pass on their extra motion to particles all along the bar. Now this process is called conduction. When the faster particles pass on their extra motion to particles all along the material. So this is called conduction. So here we have some points to remember. More thermal energy is transferred every second if, number one, the temperature difference across the ends of the bar is increased, if, number two, the cross-sectional area of the bar is increased, and lastly, if the length of the bar is reduced. So then more thermal energy would be transferred every second. So this was conduction, the movement of particles. Not actually, so this was conduction. When particles move to pass on their energy to other slower moving particles. Now that we've understood conduction, we can understand conductors and insulators as well. Now this is pretty easy to understand. Some materials are much better conductors than others, but some conductors are very poor, so they are called insulators. Many materials are in between the two. They are called semiconductors. Example of conductors are metals. Metals are the best thermal conductors, but then non-metal solids tend to be poor conductors. So do most liquids. Gases are the worst of all. Many materials are insulators because they contain tiny pockets of trapped air. You use this idea when you put on lots of layers of clothes to keep you warm, because the air gets trapped in your clothes and they keep you warm. You can sometimes tell how well something conducts just by touching it. For example, a metal door handle feels cold, but it quickly conducts the thermal energy away from your hand and it comes back to a normal temperature. So we can say that metal is a good conductor. Another example is a polystyrene tile. This polystyrene tile feels warm because it insulates your hand and stops it losing thermal energy. So we might get confused. We might say that plastics are better conductors compared to metals because when we touch plastics, they are warm. But when you touch a metal, they are cold. But metals feel cold because our hand is warmer than those metals. If we touch a metal, it quickly becomes equal to the temperature of your hand as well. It never stays cold for long. So what happens is that metal conducts the thermal energy away from your hand quickly. So metals are a good conductor and plastics are insulators. So here we have an experiment which shows that water is a poor thermal conductor. So we have some ice trapped in a gauze and we have water all over this tube. So this ice is inside the water, but it is trapped to the bottom of the tube by this gauze, metal gauze. And what is happening is that the water at this point of the tube is boiled using a Bunsen burner. It's not boiled over here, but it is being boiled over here. So you can see that the water at the top of this tube can be boiled without the ice melting, which means that water is a poor conductor of energy. This means that the particles in water are not passing on the thermal energy from here to here. They're not moving forward, and that is the reason this ice doesn't melt. So we can also compare good thermal conductors by each other, like compare their conductivity. How we can do that is, for example, we have 4 metals. We have steel, iron, aluminium, and copper. We have rods of these metals, one single rod of each metal. And what we do is that we coat these rods with a thin layer of wax when they are cold. Then we attach these rods to a small box which contains boiling water. Now we wait till the wax of these rods start to drip off. The length of the melted wax will show which material is the best conductor. So in these 4 metals, copper, aluminium, iron and steel, we have copper, which is the best conductor because solid wax melts faster compared to aluminium's wax and steel's wax. So copper is a good conductor. After copper we have aluminium, which is a good conductor. But copper is number 1, aluminium is second, iron is third, and then steel is the last. Because steel's wax is melting off at a very slow rate. So this is an example we can use to compare 4 good thermal conductors. Now we're going to look at how materials conduct. So when a material is heated, the particles move faster, push on the neighboring particles, and speed those up too. All materials conduct like this, but in metals, energy is also transferred by another much quicker method. So let's look at this now. Right? In atoms, there are tiny particles called electrons. So most of these electrons are firmly attached in their shells, but in metals, some are loose and free to drift between the atoms. So when a metal is heated, these free electrons speed up. As they move randomly within the metal, they collide with atoms and make them vibrate faster. So in this way, thermal energy is rapidly transferred to all parts. An electric current is a flow of electrons, so metals are good electrical conductor as well as good thermal conductors. So this is how materials conduct. Well, I would like to say this is how metals conduct. Not all materials conduct like this because not all materials have free valence electrons. So this was conduction. I hope you have understood it right away because it's so easy to understand. Conduction simply happens when faster particles in a material pass on their extra motion to particles all along the material. So it's pretty simple to understand, and we've understood conductors and insulators as well, what they are and how metals conduct. So we are going to move ahead on to understanding convection. So liquids and gases are poor thermal conductors. But if they are free to circulate, they can carry thermal energy from one place to another very quickly. Well, we might think that metals are the best conductors, but gases and liquids can also conduct. Here is what happens. So, in an experiment, the bottom of a beaker is filled with water, and it is being gently heated in one place only. So, as the water above the flame becomes warmer, it expands and becomes less dense. So the less dense water rises upwards as the cooler, denser water sinks and displaces it, which means it pushes it out of the way. So the result is a circulating stream called a convection current. This is so interesting, right? The method by which liquids conduct heat energy is convection. What happens when the liquid is heated at one place, the water which is being heated at that place becomes less dense and displaces the denser water above. So the denser water pushes it out of the way and gets warm from the flame as well. So again, the less dense water goes up and the denser water comes down. The result is a circulating stream. So this circulating stream keeps on circulating till the water is fully warmed. So this circulating stream is called a convection current. So when the water is heated, its particles gain energy and vibrate more rapidly. As the particles circulate, they transfer energy to other parts of the beaker as well. So another point to remember is that convection, it does not occur if the water is heated at the top rather than the bottom. Because what will happen is that the warmer water, which is the less dense water, would stay at the top because the water is less dense, so it will stay above the denser water. So a convection current only occurs when the container of the liquid is heated at the bottom. In the same way, we have convection in air. I'm going to just speak it out verbally and let you guys understand it. So convection can occur in gases as well as liquids. For example, warm air rises when it is displaced by cooler, denser air sinking around it. Let's take the seashore as an example. What happens is that heated by the sun, the warm air rises above the equator as it is displaced by the cooler, denser air sinking to the north and south. The result is huge convection currents in the Earth's atmosphere. These cause winds across all oceans and continents. So during the daytime, in hot sunshine, the land heats up more quickly than the sea. So warm air rises above the land as it is displaced by cooler air moving in from the sea. So in the daytime, the water is cold compared to the land. So the land is warmer than the sea. So cool air from the water sinks and the warm air from the dry land rises. Whereas in the night it is opposite. The sea becomes warmer than the land. So what happens is that the cool air from the land displaces the warm air from the sea. The sea stays warmer than the land, which cools down quickly. So warmer air now rises above the sea as it is displaced by cooler air moving out from the land. So this was an example of convection in air. Now let's look at how we use convection in the home. So for the first example is the hot water system. So this is the hot water system, as you can see. Hot water for the taps comes from a large storage tank. The water is heated by a coil of copper pipe. This is the hot water tank, and this water in the tank is heated with this coil of copper pipe. So hot water from a boiler flows through this and is recirculated by a pump. In the tank, the heated water rises to the top by convection. So in this way, a supply of hot water collects from the top down. So the tank is insulated to reduce thermal energy losses by conduction and convection. Practical systems are more complicated than the one I'm showing right here. There is additional pipe work to allow the water to expand safely when heated. Also, there may be an extra circuit for radiators. So you can see here we have the cold water supply. So the cold water comes over here, and this cold water also goes forwards to cold taps and toilet. But to heat this water up, this water goes in this hot water tank. The tank is insulated and the water in this tank is heated from this boiler. Then the hot water is sent out from here. So this is the hot water system. The next example are these. These are the two next examples. The refrigerator, as you can see. So what happens in the refrigerator, there are convection currents in the refrigerator as well. What happens is that cold air sinks below the freezer compartment. This sets up a circulating current of air which cools all the food in the refrigerator. The second example is room heating. So we have a fireplace over here. So warm air rising from this fireplace or conductor heater or radiator, whatever it may be, carries thermal energy all around the room, though unfortunately the coolest air is always around your feet. So this is another example of convection current. Well, on Earth we are warmed by the sun. Its energy travels to us in the form of electromagnetic waves. These include invisible infrared waves as well as light, and they can travel through a vacuum. So they heat up things that absorb them, and so are often called thermal radiation. So all objects give out some thermal radiation. The higher their surface temperature and the greater their surface area, the more energy they would radiate per second. Thermal radiation is a mixture of different wavelengths. So warm objects radiate infrared, but if they become hotter, they also emit shorter wavelengths, which may include light. That is why a radiant heater or grill starts to glow red hot when it heats up. Now we're going to look at some emitters and absorbers. By emitters and absorbers, we mean the emitters and absorbers of radiation. So some surfaces are better at emitting, which means sending out thermal radiation, than others. For example, a black saucepan cools down more quickly than a similar white one because it emits energy at a faster rate. So good emitters of thermal radiation are also good absorbers. Here we can see that matte black is the best emitter, the best absorber, and the worst reflector. From here we go to worst emitter, worst absorber, and best reflector, which is silver. Good emitters of thermal radiation are also good absorbers. White or silvery surfaces are poor absorbers because they reflect most of the thermal radiation away. So that is why in hot, sunny countries, houses are often painted white to keep them cool inside. And also why people prefer to wear light colors in hot days, because white reflects thermal radiation. Now here we have two different experiments we can do to check which is the best emitter and the worst emitter. So first we're going to see comparing emitters. Then we're going to compare absorbers. So for comparing emitters, we have this experiment. So here we have a metal cube, and this metal cube is filled with boiling water, which heats the surfaces to the same temperature. The surfaces of this cube are different. Over here we have a shiny white surface, we have a matte black surface, a dull silver surface, and a shiny silver surface. So thermal radiation detector, as you can see, this is the one, is placed in turn at the same distance from each surface, and the meter readings are compared. So this is a really interesting experiment. Check out which is the best emitter. The best emitter is of course going to be matte black surface, because it's matte, it's not shiny, and it's black. And the worst emitter is going to be the shiny silver surface, not the dull silver surface, because shiny objects reflect most of the light, most of the thermal radiation, So this was the experiment we used to compare emitters. Now we're going to look at the experiment we do to compare absorbers. So the metal plates, as you can see, these three, are placed at the same distance from a radiant heater. This is the radiant heater. So to find out which surface absorbs thermal energy most rapidly, the rises in temperature are compared. So all of these plates have their thermometers attached to them. We have a shiny silver plate, a matte white plate, and a matte black plate. And there's a heater in between all of them. So they are placed with the same distances from each other. So what do you think, which one is going to be the best absorber? Of course, the matte black one, because we have read that matte black is the best absorber and silver and white are the worst absorbers. So matte black is going to be the best absorber. This is the experiment we used to compare absorbers. So these are really interesting experiments we can do to compare emitters and compare absorbers. And this is the chart which tells us which one is the best and which is the worst. So if an object absorbs thermal radiation faster than it radiates, it heats up. And if it radiates faster than it absorbs, it cools down. So the temperature changes until a balance is reached. This is true of the Earth, which is absorbing incoming radiation from the sun, but also radiating energy into space. So without an atmosphere, the Earth's average surface temperature would be minus 18 degrees centigrade. However, carbon dioxide and water vapor in the atmosphere trap some of the incoming energy. As a result, the average surface temperature is closer to 15 degrees centigrade. So, over the last 60 years, the amount of carbon dioxide in the atmosphere had gone up more than 30%, mainly due to the increased burning of fossil fuels. And as a result, the flows of thermal radiation are out of balance, as the Earth is slowly warming up. So global warming is when the Earth starts to warm up slowly, and due to the increased burning of fossil fuel, there is more percentage of carbon dioxide. The percentage of carbon dioxide has increased in the atmosphere. So the Earth is slowly warming up, which means that we have global warming. So in many situations, the transfer of energy takes place by more than one process. Let's think about two examples. A car has a radiator to stop its engine overheating. Unwanted thermal energy is carried by liquid coolant to an array of pipes conducted to metal fins, then carried away by air flowing across the fins. So only a little of the energy is transferred by radiation. This was one example. We have another example. When you stand in front of a wood-burning stove, you will feel the warming effect of the thermal radiation coming from it. However, the room is mostly warmed by air that is heated by the stove, then rises and circulates by convection. So, in this example, we can see that the transfer of energy is taking place by more than one process, which is we have thermal radiation coming from the stove. This is thermal radiation. This is one process. The room gets warmed up by convection. So that's another process. Convection is also involved in this. So this was the example of transfer of energy. So now that we've understood thermal radiation and convection, we are going to move ahead onto understanding evaporation. So even on a cool day, rain puddles can vanish and wet clothes dry out. So the water becomes an invisible gas, which is called water vapor, which drifts away in the air. When a liquid below its boiling point changes into a gas, this is called evaporation. What evaporation is, when a liquid changes into a gas below its boiling point, this is called evaporation. So for example, when we put water in a pot and leave it on stove to let it boil, we see that a lot of steam starts to come up from the water even though the water is not boiling. So at that stage, the water is below its boiling point and it still changes into a gas. What happens is that the molecules in the water start to move rapidly and they start to just collide with each other and push each other apart. And so the particles on the surface of the water leave the water surface. Basically, they start to go up into air, and by pushing each other and vibrating, they move so wide apart that they turn into a gas. Because liquid particles are close, but when they turn into a gas, they are far apart from each other. Okay, so this is evaporation. Now we're going to look at the several ways of making a liquid evaporate more quickly. From this, we are going to get the answers about how rain puddles can vanish and wet clothes can dry out even on cool days. So, firstly, we have increased the temperature. Now, we all know wet clothes dry faster on a warm day because more of the particles have enough energy to escape. Because of heat energy, the particles move faster, so they have enough energy to escape because of the temperature. The second point is increase the surface area. So, water in a puddle dries out more quickly than water in a cup because more of its molecules are close to the surface. So there is a large surface area and there's less water depth in a puddle. The third way is to reduce the humidity. So if air is very humid, this means that it already has a high water vapor content. So in humid air, wet washing dries slowly because molecules in the vapor return to the liquid almost as fast as those in the liquid escape. So in less humid air, wet washing dries more quickly. And lastly, blow air across the surface. So wet clothes dry faster on a windy day because the moving air carries escaping water molecules away before many of them can return to the liquid. So here we have the answer to the question, how wet clothes dry out even on a cool day. So this was evaporation, a very simple process. And these were the several ways of making a liquid evaporate more quickly. Now we're going to understand boiling. We all know what boiling is. So boiling is a very rapid form of evaporation, in simple words. So when water boils, vapor bubbles form deep in the liquid. They expand, rise, burst, and release large amounts of vapor. So even cold water has tiny vapor bubbles in it, but these are squashed by the pressure of the atmosphere. So at 100 degrees centigrade, the vapor pressure in the bubbles is strong enough to overcome atmospheric pressure. So the bubbles start to expand and boiling occurs. Well, do you know that evaporation has a cooling effect as well? For example, if you wet your hands, the water on them starts to evaporate. And as it evaporates, it takes thermal energy away from your skin. So your hands feel cold. Now, the kinetic energy explains the cooling effect like this. If faster particles escape from the liquid, slower ones are left behind. So the temperature of the liquid is less than before. So simple, right? The faster moving particles have more energy in them, so they leave the liquid, and the slower ones are left behind, which have less energy. So the temperature of the liquid is less than before. Refrigerators also use the cooling effect. So the process works like this. In the pipes in the freezer compartment, a liquid called a refrigerant evaporates and takes thermal energy from the food and air. The vapor is drawn away by the pump, which compresses it and turns it into a liquid. This releases thermal energy, so the liquid heats up. The hot liquid is cooled as it passes through the pipes at the back, and the thermal energy is carried away by the air. Overall, thermal energy is transferred from things inside the fridge to the air outside. So this is refrigerators using the cooling effect. We also have sweating as an example. Sweating also uses the cooling effect of evaporation. So you start to sweat if your body temperature rises more than about 0.5 degrees centigrade above normal. So 0.5 degrees centigrade is normal, and when we go above this, we start to sweat. The sweat, which is mainly water, comes out of tiny pores in our skin. So as it evaporates, it takes thermal energy from our body and cools us down. So on a humid day, sweat cannot evaporate so easily. So it is more difficult to stay cool and comfortable. So now that we understood boiling, evaporation, now that we've understood both of these processes, we are going to move ahead on to understanding condensation. So condensation is also a process like boiling in evaporation. So when a gas changes back into a liquid, this is called condensation. For example, cold air can hold less water vapor than warm air. So if humid air is suddenly cooled, some of the water vapor may condense. It may become billions of tiny water droplets in air. We see as clouds, mist, or fog. Or it may become condensation on windows or other surfaces. If condensation freezes, the result is frost. So condensation basically happens when a gas changes back into a liquid. Like when we take a cold bottle of juice out from the fridge and we leave it on the counter for 10 minutes, then you will see that there would be many water droplets forming on the bottom. Cold air can hold less water vapor than warm air. So if humid air is suddenly cooled, some of the water vapor may condense. We can see frost. Frost is also the result of condensation. When condensation freezes, it becomes frost. Condensation can also be seen on mirrors. When we breathe on a mirror or glass, condensation comes. The air from our mouth condenses on the glass and it turns into water. Clouds in the sky are also a result of condensation, or steam as well. Steam from a kettle or food being cooked is also vapor itself. It's also an example of condensation. A change from liquid to gas or a gas to a liquid is called a change of state. A change from liquid to a solid is also another change of state. It is solidification. And water freezing is an example. When it happens, the particles continue to vibrate but do not have enough energy to overcome their bonds and change positions. Okay, so this was another small process just like evaporation and boiling. Now that we've understood all these different processes like boiling, condensation, and evaporation, we can move ahead onto understanding specific heat capacity. So, specific heat capacity, what is this? So, if a material takes in thermal energy, then unless it is melting or boiling, its temperature rises. However, some materials have a great capacity for absorbing thermal energy than others. For example, if you heat a kilogram each of water and aluminium, the water must be supplied with nearly 5 times as much energy as the aluminium for the same rise in temperature. So this basically tells us that water has a higher specific heat capacity than aluminium. Because water can absorb thermal energy more than aluminium, then water is supplied with nearly 5 times as much energy as the aluminium for the same rise in temperature. So scientifically speaking, water has a specific heat capacity of 2400 joules. 400 joules per kilogram degree centigrade. Whereas aluminium has a specific heat capacity of only 900 joules per kilogram degree centigrade. So this is what it basically means, that water can absorb more heat compared to aluminium. The unit of specific heat capacity is joules per kilogram degree centigrade. It's a very big unit, isn't it? Well, here we have some other specific heat capacities as well in this table. Water specific heat capacity is 4200 joules per kilogram degree centigrade. Alcohol has 2500 joules. Ice has 2100 joules. Aluminium is 900 joules. Concrete is 800 joules. Glass is 700 joules. Steel is 500 joules and copper is 400 joules. So copper has the least specific heat capacity in all of these materials. Water has the highest specific heat capacity. So the energy that must be transferred to an object to increase its temperature can be calculated using this equation. So in this equation, we have energy transferred equal to mass multiplying by specific heat capacity multiplied by temperature change. In symbols, we write it as energy transferred is equal to mc delta temperature. So m represents mass in kg, c is the specific heat capacity in joules per kg degree centigrade, delta temperature represents the change in temperature in degree centigrade or in Kelvin. So the same equation can also be used to calculate the energy transferred. So for example, if 2 kg of water cools from 70 degrees centigrade to 20 degrees centigrade, how much thermal energy does it lose? So in this case, the temperature change is 50 degrees centigrade because you minus the initial reading with the previous reading, 70 minus 20, and we get 50 degrees centigrade. So we put this equation, energy transferred is equal to mc delta temperature, and what we get is 2 multiplied by 42, because the specific heat capacity is 4200 of water, and 2 is the mass given for water, and the change in temperature is 50 joules. So we multiply all of these together, and what we get is 420,000 joules. So this is the answer to this question. It is pretty simple to use this equation. Now that we've understood specific heat capacity, the equation we use to measure specific heat capacity, we're going to understand what thermal capacity is. This is also related to specific heat capacity. So the quantity massed into specific heat capacity is called thermal capacity. No change in temperature. We just multiply specific heat capacity with mass and we will get thermal capacity. For example, if there is 2 kg of water in a kettle, then thermal capacity of the water would be 2 multiplied by 4200 and 8400 joules per degree centigrade. This is the thermal capacity of the water. So this means that for each 1 degree rise in temperature, 8400 joules of energy must be supplied to the water in the kettle. A greater mass of water would have a higher thermal capacity. Now we're going to look at how we're going to measure specific heat capacity. So, as you can see here, the beaker contains 0.5 kg of water. When the 100 watt electric heater, this one, is switched on for 230 seconds, the temperature of the water rises by 10 degrees centigrade. So from these figures, a value for the specific heat capacity of water can be calculated. So here we have the energy transfer to water equation. This is equal to mc delta temperature. And energy supplied by heater is equal to power into time. We know this equation, we've learned this from the previous chapter. So we first find out the energy supplied by the heater. We multiply 100 by 230, 100 watt electric heater, and it is switched on for 230 seconds. So we multiply them together and we get 23,000 joules. So 0.5 kg multiplied by the specific heat capacity and multiply by 10, which is the temperature rise, and we get 23,000. So when we rearrange this equation, we will get 4600 joules per kg degree centigrade, rearranged and simplified. So to find out the specific heat capacity of aluminium or any other metal rather than liquid, the method would be the same, except that a block of aluminium is used instead of water. The block has holes drilled in it for the heat and thermometer. As before, C is calculated from this equation. Power into time is equal to mc delta temperature. It's the same equation. Okay, so because of its high specific heat capacity, water is a very useful substance for storing and carrying thermal energy. So for example, in central heating systems, water carries thermal energy from the boiler to the radiators around the house. In car cooling systems as well, water carries unwanted thermal energy from the engine to the radiator. Another example is that night storage heaters. They use concrete blocks to store thermal energy. Although concrete has a lower specific heat capacity than water, it is more dense, so the same mass takes up less space. Electric heating elements heat up the blocks overnight using cheap off-peak electricity supplied with a special meter. So the hot blocks release thermal energy through the day as they cool down. So this was specific heat capacity. It's a very simple thing to understand. Now that we've understood specific heat capacity, we are going to move ahead on to understanding latent heat. So water could be a solid, a liquid, or a gas called water vapor or steam. These are its 3 phases or states. So, solid to liquid. So this is a graph here which shows what happens to its temperature. So while melting, the ice goes on absorbing energy, but its temperature does not change. It stays at 0 degrees centigrade, which is the melting point. The solid ice temperature increased from -20 to 0 degrees centigrade, and this is the point where the melting occurs. And all of a sudden it turns into a liquid, but during melting, the ice is no longer taking in energy. It is still at 0 degrees centigrade, which means that it is not heating up anymore, and still it melts. So what happens? The energy that is absorbed is called the latent heat of fusion. So this latent heat of fusion is needed to separate the particles so that they can form the liquid. If the liquid changes back to a solid, the energy is released again. So this is the latent heat of fusion. Now, ice has specific latent heat of fusion of 330,000 joules per kg. This means that 330,000 joules of energy must be transferred to change each kilogram of ice into liquid water at the same temperature, which is 0 degrees centigrade. So for any known mass, the energy transferred would be calculated using this equation. Energy transferred is equal to mass into specific latent heat. In symbols, we write it as mL. Capital L is used to represent specific latent heat. So for example, if 2 kg of ice is melted, obviously at 0 degrees centigrade, energy transferred is equal to mL, and would be equal to 2 into 330,000 joules per kg. And my answer would be 660,000 joules. So let's do a question over here. So you can see we're going to measure the specific latent heat of fusion of ice here. So as you can see, we have a funnel over here and a beaker. There is ice in this funnel. We also have electric heater inside this ice. So the ice is being melted in the heater. So in the experiment, a 100-watt heater is switched on for 300 seconds. By weighing the water collected in the beaker, it is found that 0.10 kg of ice has melted. So from these figures, a value of L, which is the latent heat, can be calculated. Here we have the equation. Energy transferred when ice melts is equal to mL, which is equal to 0.10 multiplied by L. So 0.10 is the mass and latent heat is to be found. Now energy supplied by heater is equal to power into time, which is 100 watts into 300 seconds, and we would get 30,000 joules. Okay, so 0.10 multiplied by L would be equal to 30,000. So when we rearrange this equation, we will get 300,000 joules per kg. So the specific latent heat, so what we do is that we rearrange the equation. So right now the equation is energy transferred is equal to mL, m into L. So we're going to remember that triangle I used to tell you about again. We place m and L because they are multiplying below energy transferred, and place a multiplication sign in between. Now what do we want here? We want the latent heat of fusion. So we hide the L sign, and what we will get is energy transferred dividing by mass. So this is how we rearrange the equation. We divide energy transferred by the mass, and we would get 300,000 joules per kg. So the specific latent heat of fusion of ice is 300,000 joules. So this is how we measure the specific latent heat of fusion of ice. So this method makes no allowance for any thermal energy received from the funnel or surroundings. So the value of L is only approximate. Now we're going to look at liquid turning into a gas. So if you heat water in a kettle, the temperature rises until the water is boiling at 100 degrees centigrade and then stops rising. So if the kettle is left switched on, the water absorbs more and more thermal energy But this just turns more and more of the boiling water into steam, still at 100 degrees centigrade, so the temperature doesn't change. So the energy absorbed is called latent heat of vaporization. That at this temperature, the water's temperature doesn't increase any further, it just keeps on turning into steam till it dries out completely. So the energy absorbed is called latent heat of vaporization. Most of this latent heat of vaporization is needed to separate the particles so that they can form a gas, but some is required to push back the atmosphere as the gas forms. So this is the latent heat of vaporization. Before we understood about latent heat of fusion, which was when solid turns into a liquid. So water has a specific latent heat of vaporization of 2300,000 joules per kilograms. This means that 2300,000 joules of energy must be transferred to change each kilogram of liquid water into steam at the same temperature, which is 100 degrees centigrade. So to calculate the energy transferred when any known mass of liquid changes into a gas at the same temperature, use the equation which we use for latent heat of fusion as well, except for that L is now going to be the specific latent heat of vaporization. The whole equation is going to be the same. So, are you ready to do another question related to specific latent heat of vaporization? Of course you are. It's just as simple as it was before the latent heat of fusion. The equation is going to be the same except for L is now going to be representing latent heat of vaporization. So in this experiment you can see the can contains boiling water. This is the can. When the 100-watt heater has been switched on for 500 seconds, this is the heater. The change in mass balances reading shows that 0.020 kg of water has boiled away. So from these figures, a value of L can be calculated. So we have the same equation here. Energy transferred when water is vaporized is equal to M into L, which is equal to 0.020 multiplied by L. So energy supplied by heater is equal to power into time. We are again going to multiply 100 by 500 to get the energy supplied by heater, and we'll get 50,000 joules. So 0.20 multiplied by L is equal to 50,000 joules, which gives L equal to 2500,000. Simple, right? We just rearrange the equation again. What would we do here to get the latent heat of vaporization? We would divide 50,000 by 0.020 and we will get 2500,000. So the specific latent heat of vaporization of water is 2500,000 joules per kg. It's just the same as for latent heat of fusion of ice, except for that it is now latent heat of vaporization. Before we also did the same thing. We arranged the equation to find the latent heat. So this was the specific latent heat of vaporization of water and the specific latent heat of fusion of ice. So in this chapter, we learned about solids and liquids and gases. We one by one understood solids structure, the structure of solid, the structure of liquid, and the structure of gas. After this, we understood the energy of particles, the total kinetic and potential energy of all the atoms or molecules in a material. And this energy is called internal energy. We understood thermal energy, and then we understood the Celsius scale, the temperature scale. The unit of temperature is degrees Celsius. After this, we understood that the Celsius scale has two fixed points, the 0 degree centigrade and 100 degrees centigrade. Then we understand the thermometer, different types of thermometers, how every thermometer depends on some property or characteristic of a material that varies with temperature. We understood two different thermometers here as well, electrical, which have electrical properties. After this, we understood what temperature is. We understood the Kelvin scale. We differentiated between the Celsius and Kelvin scale. Then we understood thermal expansion and how it can be important to know how much materials will expand when we are choosing them for particular jobs. Then we looked at some examples of thermal expansion, like the bimetallic strip. Then we understood the difference between water and ice. Then we read how pressure, volume, and temperature are linked together. That when temperature increases, pressure also increases if the volume is kept constant. After this, we understood conduction. After this, we understood what conductors and insulators are, the difference between them, which are good conductors, which are bad conductors, what metals are good conductors, what metals are good insulators. We understood that water is not a good conductor by this example. We also saw how metals conduct, the free valence electrons of metals, how they help to conduct. Then after conduction, we understood convection, convection currents. We looked at some examples of convection currents in everyday life. Then we understood thermal radiation, the best emitters of thermal radiation and the best reflectors, worst absorbers or worst emitters of thermal radiation. And after this, we understood what evaporation was. The several ways of making a liquid evaporate more quickly. And then we understood boiling. Then we understood the cooling effect of evaporation. After this, we understood condensation. And after this, we understood specific heat capacity. We understood the equation of specific heat capacity. We did a question related to it. How we can measure specific heat capacity, we understood it. And then we understood latent heat. We understood the latent heat of fusion, how we use the equation to measure the latent heat of fusion, or latent heat to measure the latent heat, and we also did a question related to it. And then we understood the latent heat of vaporization. We did a question again. We used the same equation, except for that L now stands for latent heat of vaporization of water. So this was our 5th chapter. As you can see, we have completed it successfully, and it was a very interesting chapter as well. Thermal effects. So our 6th chapter is going to be about waves and sounds. So I'll see you in the next video in the next chapter.